All right, so the next part of this, we will continue to evaluate and quantify the forces involved in uniform circular motion. Now, in the last section, we just said that the net force is mv squared over r. We're going to continue to evaluate that now, but I'm going to refer to it quite often as, instead of the net force, I'm going to call it the centrifugal force. And the centrifugal force is not a real force. It's caused by other physics things that we're going to talk about in this section. So as I refer to it, understand that it is never to be drawn in a free body diagram. It is not an actual force, but it helps us understand why some things are happening to talk about it like it is a force. All right, so let's check it out. So what is the centrifugal force? Now, if I'm sitting in a car and that car turns a corner quickly, I get pushed. Here I am. I'm in motion here, and I'm going forward, and I feel like I'm getting thrown into the door, and the door provides a push back. That push back causes me to be able to turn. That is my net force. But what I feel is my body trying to keep moving ahead, and I feel as the car turns, I feel like I'm being thrown to the outside. That is the centrifugal force. It's not a real force. It will never appear on a free body diagram, and it's never included in Newton's laws, okay? So what is it then? Quite simply, it's your inertia. And that's put very nicely on this picture here. My body wants to keep going forward, but the car is turning around me, so I feel like I'm being thrown out. But really what's happening is my body's in motion, and it wants to stay in motion. So my inertia is what causes this quote-unquote centrifugal force. And then as I'm being thrown forward, the door pushes back on me, and that's what causes my centripetal acceleration. So as we're taking a look at circular motion, we do get additional phenomenons of apparent weight. And we've looked at apparent weight already, and we've said that apparent weight is equal to the normal force. So our normal force is what pushes back from the surface. And we can actually evaluate a few different things. Here we have a picture of a loop-de-loop. And again, our normal force is what's going to be the force that supports us. And that'll change based on a couple different factors. So let's take a look at two different points in a loop. So if I'm at the bottom of a loop, here is my free body diagram for what's going on. My weight is down. My weight is still straight down. But I have a normal force that's going up. And the net force, because the acceleration is towards the center of the circle, the net force is also to the center of the circle, which means that my normal force is larger than my weight. And if I look at the math behind it, then there's my normal force, there's my weight. The weight's actually in the negative direction, but those two forces have to equal my net force, which is mv squared over r. So my apparent weight equals my actual weight plus mv squared over r at the bottom of the loop. Now, that's not right before or right after. It's strictly at the exact bottom point. And the reason is your weight changes as you go through a loop. The components of it change, and it makes it a little bit more complex. So we'll only look at the top and the bottom. But this makes sense, because if I think about in a roller coaster, I'm going to draw a really crappy roller coaster. I go up, I come down, and I go around this loop. And as I'm entering this part of the loop, I feel like my body's being compressed. I have a large normal force because of that centripetal acceleration towards the center of the circle. What about at the top of the loop? Well, if I'm going up, here's my loop again. At the top of the loop, my normal force is down and my weight is down. This gets way more confusing, but the sum of the forces is still my normal force and my weight. But in this case, they're both in the negative direction. So if I solve for my normal force, it's the net force minus the weight. Okay, well let's think about that. If the net force is equal to the weight, then this will actually become 0. And just for that brief moment, I will appear weightless if I'm going just slow enough that my normal force equals my weight. Okay. As I start to increase that velocity, I start to feel heavier. The faster I go, the heavier I go, or heavier I feel, I should say. And that will never, ever cap out. I can just feel heavier and heavier based on how fast I go. Now, it is important to mention, the last little concept is what happens when we have our velocity here, and this number is smaller than the weight. And the answer is, I can't go around the loop because my weight is pulling me down. So instead, I'm going around the loop, I can't make it, and I just fall. Okay? That would be a really crappy roller coaster. But we'll talk about that as it's known as the critical velocity, and we'll talk about that in this segment. So as the car goes slower, there becomes a point where the normal force becomes 0. This doesn't mean that there's no velocity. It just means that it's just barely fast enough to overcome gravity and make it around the loop. Any slower, and the weight of the cart would be too large, and the car would fall off the track. This is known as the critical speed. So when they are exactly equal to each other, I can set them equal to each other, and I get this equation that the velocity, I call this the critical velocity, equals the square root of GR. That'll actually come up a couple times, but that is the minimum velocity needed to make it around a circle or a loop. So we're going to take a look in class tomorrow, just a quick little demo where I drop a ball and it rolls down an incline, and depending on how high I drop the ball, it may or may not make it around the loop. So it might make it to this and then fall straight down. It might make it only to here and fall down and back, or it's going to just barely make it around the loop and then go all the way around. And that's the critical velocity. So we'll take a look at that tomorrow. This is a great video. I vote we watch this tomorrow. Someone just remind me just in case. So hopefully someone is watching this video before class and they say, hey, let's go ahead and watch that video. As a matter of fact, just go ahead and raise your hand and say, hey, don't forget to watch the video, and I will give you some, I'll give you 5 points of lab extra credit if you are the first person to tell me to watch the video. Just a little encouragement for you as we start the day off tomorrow. All right, so here's a partner problem, and this is just going to utilize that concept that the critical velocity, C-R-I-T-I, oh my God, equals the square root of GR. Okay, so that's what we just derived a couple minutes ago. And it says a handful of professional skaters have taken their skateboard through an inverted loop on a full pipe. Here's our diameter. What is the minimum speed that a skater must have? And that's going to be utilizing this equation right here. We'll take a look at that tomorrow. Here's another quick check. We have a physics textbook swings back and forth as a pendulum. Which is the correct free body diagram? Well, as I know, I have a weight force going down and in this case, a tension force going up. There has to be a centrifugal acceleration because it's going around a curve, which means there has to be a net force, which means that the tension has to be greater. And this actually makes sense. The faster you swing a textbook, the more tension there is in that rope, and eventually it could break. But that is that concept right there. Another quick check. Now we're going over a hill. So I have a larger downward force because it's, again, the direction of the net force. And as I go over the hill, your weight is larger than your normal force, and you appear to be lighter. So tomorrow, we'll take a look at going over a hill, going in a dip, bottom of the loop, top of the loop, 4 specific examples about apparent weight. A huge application of this quote-unquote centrifugal force is a centrifuge. A centrifuge is a machine that rotates very, very, very fast, and because there's this inertia of the fluid or whatever it is you're analyzing, it actually separates out based on mass because the different masses experience a different force, and that leads into density, because density, of course, is mass over volume. So something with a heavier mass experiences a greater force and gets pushed to the bottom. And this is how they separate, for example, they separate blood from plasma. Plasma is more of a liquid or a less dense fluid. So it separates out because of those different forces. One of the ways you can actually try this yourself is if you spin your own arms around your body extremely quickly. This causes the blood to undergo a quote-unquote centrifugal force, and it gets pushed out to your fingertips. And if you do this, that'll actually cause your fingertips to turn like a brighter red. One of the survival skill, I guess, if you will, if your fingers are losing feeling because you're stuck in the wilderness, this gets into, I believe, oh God, who is it? Is it? I think Jack Frost is not right, but it's a Jack something or another. It's a short story. Oh man, Jack. It's a short story about a dude in the wilderness. He's like trying to get into find a gold mine, and it's like going through the Yukon Territory. It's all about starting a fire. In fact, that's what it is. It's called To Start a Fire. I got it. To Start a Fire by Jack London. I'm pretty sure that's correct. Again, if you remind me, I will maybe I'll pull up a quick little video of this short story. The video itself has no dialogue in it, or very little dialogue in it. But what was I talking about? Oh yeah. So if your fingers are going numb, spin them around in a circle, get the blood flowing, and then you could hold a match to start a fire. I apologize for that minute and 26 second. What's the word I want? Trailing off, side conversation, whatever. All right. So here's a quick little conceptual example of an ultracentrifuge. Now, an ultracentrifuge, just like a regular centrifuge, produces this centripetal acceleration, and these actually can create a centripetal acceleration of up to 250,000 Gs. And they do that to separate out different samples. So they can have this 3 kilogram sample, which only weighs 3 grams, and it spins at about 50,000 RPMs, and the math is all right above it to understand what you have to do to get that acceleration based on the frequency and centripetal acceleration, of course, v squared over r, but also getting into the concept that acceleration is the quantity of 2 pi f quantity squared r, and that actually solves for how fast it has to rotate. And then the apparent weight of that sample is actually 7,400 newtons. 7,400 newtons, that's 740 kilograms, which is over 1,500 pounds. So a 3 gram sample undergoing this feels like it weighs 1,500 pounds. And that's how they're able to create such that large force to separate stuff out. So that's just like I said, it's examples and just explaining what this quote-unquote centrifugal force is. And it's not a real force, but it's something that gets felt because of your inertia. So we'll take a closer look at this again tomorrow, and we'll talk a little bit more about some of the applications of this, specifically getting into planetary and gravitational concepts, and we'll do that in the next segment.